Welcome to today's explainer. So, have you ever measured a room twice for a new couch and somehow gotten two slightly different numbers? Well, today we're going to demystify a fundamental truth of science, engineering, and data collection. And that truth is, your measurements are never, ever perfectly accurate. Seriously. Whether you're running a massive industrial measurement system, conducting a highly controlled scientific experiment, or honestly, just tracking everyday data, the measured value of a quantity is always going to differ at least a little bit from its true value. Today, we're exploring the anatomy of measurement errors to understand exactly why these inaccuracies happen, and more importantly, how we can systematically conquer them.
Okay, let's dive right in. Here's our roadmap for today. We'll start with the reality of measurement, before breaking down the three major culprits behind flawed data: gross errors, systematic errors, and random errors. Finally, we'll wrap up with a practical toolkit for minimizing these variations. Section 1. The reality of measurement. Unavoidable variations. Okay, so we really need to completely shatter a common misconception right off the bat. Measurement errors are not necessarily mistakes made by the observer. Let me say that again because it's absolutely crucial. Errors are not just personal failings. Instead, they're unavoidable variations. They pop up due to the physical limitations of the instruments we're using, the environmental influences surrounding us, the observational methods we employ, and, just simple random fluctuations in the universe. Recognizing that measurement error is an inherent part of the process, rather than just a personal screw-up, fundamentally shifts how we analyze and correct our data. And this classification map brilliantly illustrates exactly how these unavoidable variations break down. It's like a giant puzzle. Measurement errors essentially fall into three major families: gross, systematic, and random. Systematic errors then further branch out into instrumental, observational, and environmental. We're going to explore every single one of these boxes, starting right over on the far left.
Section 2. Gross errors. Human blunders.
Picture this. You're looking at a voltmeter. The needle clearly points to 25.6 volts, but you're in a rush, maybe a little distracted, and you write down 52.6 V. That right there? That's a gross error. It's a large, clumsy mistake caused directly by a human factor during the measurement, recording, or calculation phase. Other examples might include writing down a temperature in Fahrenheit when the mathematical formula explicitly requires Celsius, or literally just completely forgetting to calibrate an instrument before you even begin.
So gross errors produce completely abnormal results that differ wildly from what you'd expect. The causes are pretty straightforward: incorrect reading of measuring instruments, recording wrong values, improper use of the instruments, computational mistakes, or even just using blatantly damaged equipment. But here's the single most important thing to remember about gross errors. They're usually entirely avoidable. They happen because of carelessness, a lack of experience, or improper handling. We fix these with proper training, careful observation, cross-checking calculations, and ideally utilizing automated data acquisition systems to just take the whole human element out of the recording process entirely.
Section 3. Systematic errors. Predictable patterns. Notice the stark contrast here. While gross errors are erratic, abnormal human mistakes, systematic errors are incredibly consistent. We're talking about repeatable deviations that occur in the exact same direction during measurements. They cause your measured value to differ from the true value by a fixed, mathematically predictable amount. They don't vary unpredictably, they follow a strict pattern. And because they consistently skew your data in one direction, they severely impact the overall accuracy of your measurements.
Section 4. Types of systematic errors. 4 distinct sources.
So the crucial point is that a systematic error can sneak in from 4 distinct sources. First up, instrumental errors. These arise from imperfections or faults in the measuring instrument itself. Think improper calibration, mechanical wear and tear, or aging components. Second, environmental errors. Your surroundings actually matter a lot. Temperature changes, humidity, dust, and even magnetic fields can consistently warp your readings. Third, observational errors. Now, this isn't just writing down the wrong number. This is a physical limitation like parallax error, viewing an analog meter from an angle so the needle looks higher or lower than it truly is. And finally, theoretical errors. These happen because of the simplifications or approximations we use in our mathematical models, like purposefully ignoring air resistance in a physics calculation to make the math easier.
To really cement how a systematic error behaves, let's look at a classic instrumental example. Imagine a weighing balance showing 0.5 grams even when it's completely unloaded. This is known as a zero error. If you don't notice this, every single item you weigh is going to be exactly 0.5 grams heavier than its true value. It's consistent, it's repeatable, and it skews your accuracy in a fixed direction every single time. But here's the silver lining. Because it's consistent, if you identify it,
You can mathematically correct your entire dataset just by subtracting that 0.5 grams across the board.
Section 5. Random errors. Unpredictable chaos. Now, I want you to imagine this scenario. You are perfectly trained, you don't make a single human blunder. Your environment is perfectly controlled, your instruments are flawlessly calibrated, and your theoretical math is exact. So, what happens when you do everything perfectly, but your measured results still fluctuate? Well, welcome to the reality of random errors.
Random errors are literally the ghosts in the machine. They're unpredictable variations that happen due to uncontrollable or entirely unknown factors. They cause your measured values to fluctuate slightly above or below the true value in a completely irregular, chaotic manner. So what causes them? Things like baseline electrical noise, tiny undetectable environmental fluctuations, or microscopic mechanical vibrations. The key takeaway here is that random errors affect the precision or the repeatability of your measurements rather than their overall fixed accuracy. You can't mathematically predict them, and honestly, you can never completely eliminate them.
Section 6. Minimizing your measurement errors. Protecting your data. Let's move to our final steps and see how this builds a really cohesive strategy to protect your data. Step 1. To avoid those human blunder gross errors, automate your data acquisition wherever possible, maintain incredibly careful procedures, and always cross-check your calculations. Step 2. To fix those predictable systematic errors, you absolutely must perform regular instrument calibration, use high-quality gear, and tightly control your laboratory environments with things like temperature compensation or vibration isolation. And step 3, to combat the uncontrollable chaos of random errors, you must take multiple measurements and calculate the average. Statistical analysis and noise filtering techniques are your best friends here to smooth out those tiny, unpredictable bumps.
As we wrap up this explainer, I want to bring us full circle back to that quote from the very beginning. Errors are not necessarily mistakes made by the observer. Instead, they are unavoidable variations. By formally classifying these variations into gross, systematic, and random, we empower ourselves. We stop viewing data discrepancies as mere failures, and we start treating them as puzzles. Puzzles that can be identified, mathematically corrected, or statistically smoothed out. Armed with this structural map of measurement errors, I'm going to leave you with this. How will understanding these precise classifications change the way you approach your very next dataset? Will you double-check your zero calibration? Will you take a few extra readings just to average out the noise? Think about it. Thanks for joining me on this explainer, and as always, stay curious.